Our objective in this section is to find derivatives of functions that are given in implicit form. If we have an equation such as this one, y equals 2x squared minus 3, we sometimes say that it is an explicit function of x, since we can write y equals f of x with f of x equaling 2x squared minus 3. The equation 4x squared minus 2y equals 6 determines the same function f, since solving for y gives us negative 2y equals negative 4x squared plus 6, or y equals 2x squared minus 3, which is the same as before. For the case of 4x squared minus 2y equals 6, we say that y, or f, is an implicit function of x, or that f is determined implicitly by the equation. If we substitute f of x for y into 4x squared minus 2y equals 6, we obtain 4x squared minus 4x squared plus 6 equals 6. The last equation is an identity, since it is true for every x in the domain of f. This is a characteristic of every function f determined implicitly by an equation in x and y. That is, f is implicit if and only if the substitution of f of x for y leads to an identity. Since f of x is a point on the graph of f, the last statement implies that the graph of the implicit function f coincides with a portion or all of the graph of the equation. The method of implicit differentiation provides the derivative of any differentiable function determined by an equation in two variables. For example, the equation x squared plus y squared equals 1 determines many implicit functions. The slope of the tangent line at any points xy is given by y prime equals negative x over y, given the derivative exists. In implicit differentiation, we differentiate each term of the equation with respect to x. In using implicit differentiation, it is often necessary to consider dy dx of y to the n for some unknown function of y of x, say y equals f of x. For example, in this function right here, we would have to differentiate, we would try to find y prime, we would need to differentiate this y and this y along with the rest. So we start by taking one term at a time. 4y cubed is the derivative of that times y prime plus 3 times y prime, always include a y prime, minus 12x squared equals 5. This cancels out, the x's and that y cancels out, and then we have y prime. But we don't want y prime like this, we want it to be on its own. So first we move all the others to the other side so that this is 5 plus 12x squared. Then we factor to get y prime alone. And after that, we can find that y prime is equal to 5 plus 12x squared over 4y cubed plus 3. Now, if you wanted this just to be in terms of y prime, you could always take the original equation in terms of y and factor it back in here, but in this case that seems very unreasonable, so we leave it in this form. Use the power rule to remember all y primes. Remember that in the power rule it states that we must find if an equation g of x to the n, we must find n g of x to the n minus 1 times g prime of x. In this case, g prime of x is y prime, as we saw in the last example. Here's some more practice. To differentiate this, we must first differentiate each term, 16x. We don't need to find what is inside the x as we're not differentiating for x. So 16x plus 2y, remember the power rule, y prime, equals 0. We then move things around and find that 2y times y prime equals negative 16x, or y prime equals negative 16x over 2y. You could cancel these and write this as negative 8x over y. Another example, 6x squared plus, here's the tricky part, we need to remember our product rule here, our u and our v. So we do u times dv, which in this case is y prime, plus vy times du, 2x, plus 3y squared, y prime, equaling 0. We then move things around to the other side. So we want all the y primes on the left and all the non-y prime terms on the right. So x squared y prime is a y prime term, so is 3y squared y prime. And then the other terms, 6x squared, negative 6x squared, minus 2xy. Then we factor the y prime, and then divide and solve for y prime. And that is your solution. That's all for implicit differentiation.